Spin ice is a fascinating state of matter found in certain magnetic materials, where the arrangement of magnetic moments, spins of atoms, resembles the positional disorder of hydrogen atoms in water ice. In these materials, the magnetic ions form a tetrahedral lattice, and their spins follow a two-in, two-out rule, creating a highly frustrated and disordered system similar to the hydrogen bonding in water ice. Imagine the spins as arrows on a tetrahedron, with two pointing inward and two outward, like the hydrogen atoms around an oxygen atom in ice. This frustration leads to a multitude of possible configurations, much like the many arrangements of hydrogen atoms in ice. A striking feature of spin ice is the emergence of monopole-like excitations. When a spin flips, it disrupts the two-in, two-out arrangement, creating a pair of defects that act as isolated magnetic charges or monopoles. This is analogous to breaking a bar magnet and finding isolated north and south poles, which isn't possible in conventional magnets. These monopole-like excitations can move independently, akin to how electric charges flow in a conductor. These properties of spin ice have been confirmed through experiments like neutron scattering, revealing a rich landscape of magnetic phenomena. Understanding spin ice and its monopole-like excitations provides deep insights into magnetic frustration and emergent behaviors in condensed matter physics, with potential applications in magnetic storage, spintronics, and quantum computing. Imagine a checkerboard frozen in time. Each square, locked in place, represents a moment of stillness, a snapshot of a complex dance halted mid-motion. Instead of black and white squares, picture tiny magnets pointing up or down. These magnets, or spins, are like tiny arrows, each one pointing in a specific direction, creating a pattern that is both intricate and mesmerizing. This is the essence of spin ice, a peculiar state of matter where magnetic moments, or spins, are locked in a disordered arrangement. Unlike a neatly ordered crystal, spin ice is a chaotic jumble, a frozen frenzy of spins that defies conventional order. Like water ice with its hydrogen bonds, spin ice exhibits a similar kind of randomness. In water ice, the hydrogen atoms are arranged in a disordered manner, creating a structure that is both rigid and flexible. This randomness leads to what physicists call frustration. In the world of spin ice, frustration is not about annoyance, but about the inability of the spins to settle into a perfectly ordered state. The spins can't align perfectly, leaving the system in a state of high entropy, even at extremely low temperatures. This high entropy is a measure of the disorder and complexity within the system. This residual entropy is a hallmark of spin ice, hinting at the unusual physics at play. Even when cooled to near absolute zero, spin ice retains a level of disorder that is both fascinating and perplexing. This isn't your refrigerator magnet. While a refrigerator magnet is a simple, ordered system, spin ice is a complex, disordered one, with magnetic moments that are constantly in a state of flux. In spin ice, the magnetic moments are frustrated, unable to find a happy, ordered state. This frustration is a key feature of spin ice, leading to its unique and intriguing properties. This frustration arises from the competing interactions between neighboring spins, dictated by the ice rules. These rules govern how the spins interact with each other, creating a delicate balance of forces that prevents the system from settling into a simple, ordered state. These rules, analogous to the way hydrogen bonds arrange themselves in water ice, lead to a multitude of possible spin configurations with the same energy. This multitude of configurations is what gives spin ice its high entropy and its fascinating properties. This degeneracy is the root of the residual entropy and the source of spin ice's fascinating properties. The fact that there are many possible configurations with the same energy means that the system is constantly in a state of flux, never settling into a single ordered state. The discovery of spin ice in the late 1990s opened up a new playground for physicists to explore exotic magnetic phenomena. This discovery has led to a deeper understanding of the complex interactions that govern the behavior of magnetic materials. Unlike conventional magnets, which exhibit long-range magnetic order, spin ice materials remain magnetically disordered, even at extremely low temperatures. This disordered state is a key feature of spin ice, setting it apart from other magnetic materials. This unique characteristic stems from the underlying geometry of the crystal lattice and the frustration it imposes on the magnetic moments. The lattice structure creates a complex web of interactions that prevents the spins from aligning in a simple, ordered manner, leading to the fascinating and unique properties of spin ice. Imagine a group of children playing tug-of-war. Each child is pulling with all their might, trying to gain an advantage over the other side. The tension in the rope represents the struggle and interaction between them. Each child in this scenario represents a magnetic spin, and the rope they are pulling on symbolizes their interaction. Just as the children are bound by the rules of the game, magnetic spins are governed by the laws of physics. In the fascinating world of spin ice, the rules of the game are dictated by the underlying crystal structure. These rules enforce a two-in, two-out configuration for the magnetic spins. For each tetrahedron, which is a fundamental building block of the spin ice lattice, 2 spins must point inward and 2 must point outward. This arrangement is not just a random occurrence, but a strict rule that must be followed. This seemingly simple rule, which is analogous to the Bernal-Fowler rules in water ice, leads to a surprising amount of complexity. The interactions between the spins create a rich tapestry of behavior that is both intricate and fascinating. Now, imagine a playground full of children, each holding a magnet. These magnets represent the magnetic spins in our spin ice model. In a conventional magnet, all the magnets align in the same direction, much like well-behaved children standing in a straight line, all facing the same way. This orderly arrangement is what we typically expect. But in spin ice, the children are given a different set of instructions. They are told they can't all face the same way. This restriction creates a unique and complex scenario. This leads to a chaotic arrangement, with magnets pointing in different directions. The spins are in a state of disarray, unable to find a simple, ordered configuration. This disorder, a direct consequence of the ice rules, is what makes spin ice so intriguing. The inability to achieve a perfectly ordered state results in a rich and complex system. The frustration arises because the spins can't satisfy all the ice rules simultaneously. This conflict between the rules and the possible configurations leads to a state known as magnetic frustration. Like a puzzle with no solution, the system is stuck in a state of perpetual indecision. The spins are constantly trying to find a configuration that satisfies the rules, but such a configuration is impossible to achieve. This frustration is not just an academic curiosity. It leads to remarkable properties, such as the emergence of magnetic monopoles. These are theoretical particles that have fascinated scientists for decades. These elusive particles, never observed in isolation in nature, emerge as emergent excitations in spin ice. This phenomenon further solidifies spin ice's status as a playground for exotic physics, offering a glimpse into the fundamental nature of magnetic interactions and the potential for new discoveries. Imagine building a castle out of Lego bricks. Each brick has a specific shape and size, and the way you arrange them determines the final structure of your castle. The shape of the castle depends on the shape of the bricks. If you use square bricks, you'll get a different structure than if you use triangular or rectangular ones. Similarly, the properties of spin ice depend on the arrangement of atoms in its crystal lattice. Just like Lego bricks, the atoms form specific patterns that dictate the material's characteristics. Two common structures found in spin ice materials are the pyrochlore and kagome lattices. These lattices are like the blueprints for how the atoms are arranged. The pyrochlore lattice resembles a network of corner-sharing tetrahedra, like a three-dimensional checkerboard. This intricate pattern creates a unique environment for the atoms. This structure is found in materials like dysprosium titanate, a classic example of spin ice. Dysprosium titanate's atomic arrangement is a perfect representation of the pyrochlore lattice. The tetrahedral building blocks are crucial, as they enforce the two-in, two-out ice rule, leading to magnetic frustration. This rule means that 2 magnetic moments point into the center of each tetrahedron and 2 point out. The kagome lattice, on the other hand, resembles a basket weave pattern, with triangles connected at their vertices. This pattern is flat and two-dimensional, unlike the three-dimensional pyrochlore lattice. This structure, found in materials like Herbert-Smithite, also exhibits magnetic frustration, but with different geometrical constraints compared to the pyrochlore lattice. Herbert-Smithite's atomic arrangement showcases the kagome lattice's unique properties. The triangular arrangement of spins in the kagome lattice leads to even more complex magnetic interactions and potential for exotic ground states. These interactions can result in unusual magnetic behaviors that are still being studied. These lattices, with their unique geometries, act as the stage on which the drama of magnetic frustration unfolds. Each lattice type creates a different set of rules for how the magnetic moments interact. The arrangement of atoms dictates the interactions between spins, ultimately determining the exotic properties of spin ice. The specific layout of atoms in the lattice is what gives rise to the material's unique magnetic properties. Understanding these structures is key to unlocking the secrets of this fascinating state of matter. Scientists continue to study these lattices to uncover new insights into the behavior of spin ice and other related materials. Imagine a bar magnet with its north and south poles. Now, imagine somehow separating these poles, creating isolated magnetic charges. These hypothetical particles, called magnetic monopoles, have never been observed in isolation in nature. However, in the strange world of spin ice, something remarkable happens. Monopole-like excitations emerge. These are not true magnetic monopoles, but rather emergent excitations that behave like them. Flipping a single spin in spin ice creates a pair of north and south magnetic charges, connected by a string of flipped spins. These charges can move independently, behaving like free magnetic monopoles, even though they are ultimately connected. Scientists have detected these elusive quasi-particles using sophisticated experimental techniques. Neutron scattering, a technique that probes the magnetic structure of materials, reveals the telltale signatures of monopole excitations. Measurements of magnetic susceptibility, which quantifies a material's response to a magnetic field, also provide evidence for the existence of these unusual particles. The discovery of monopole-like excitations in spin ice sent ripples through the physics community. It provided a tangible example of emergent phenomena, where complex behavior arises from the collective interactions of simpler constituents. This discovery not only deepened our understanding of magnetism, but also opened up new avenues for exploring the fundamental nature of matter.